This is a more in-depth video than the previous one, which was just to show that the MIDI output was working. Now, this one describes the MIDI functions in detail and then moves on to the demo program, which may be of interest even if you're not a PlasMa fan. It emulates an old-school music composing machine called the Muse. Well, first, the MIDI interface. Now, this is just basic MIDI using standard note-on and note-off messages. It uses the same three I/O functions which were shown in video 9 for playing musical tones on the built-in speaker. The play note parameter contains a flag which says whether the note is an audio tone or a MIDI note. The time interval still applies, so you can initiate a MIDI note with a specific length, such as a quarter note or 16th note, except that now there are 4 bits which define the MIDI velocity. Now, I know this is less than the standard 7 bits, but the values are scaled up, so there should be enough variation for basic use. The tempo and gate time is also set with the same set note attributes function, so you don't have to worry about time delays or converting tempo to time. And just like audio notes, the system automatically stops the note when the correct time has elapsed. So for MIDI, this means it sends a note off message automatically. The third function, get note status, is used to check when the interval has finished. Now, this interval method was designed to make the programmer's life simpler and use less memory. Conventional MIDI programs usually handle their own timing and tempo conversions, so they initiate notes with infinite duration and then send a note off at some specific time later. Now, this method can cause stuck notes if you don't send the note off for some reason, so that's another advantage with the interval method. But one disadvantage is that you have to know how long the MIDI note is before you initiate it. So to cater for this conventional use, one of the play note intervals allows infinite note lengths. And there's a fourth I/O function called end note, which will send note off messages. Now, these also work with the audio note system. Okay, that's the interface. So I'll connect the MIDI output to a synthesizer and move on to the demo program. Now, as mentioned, the demo is a simulator for an old-school electronic instrument called the Muse, which appeared in the late 60s and early 70s, so it seemed an ideal candidate for PlasMa, as it's from the same era of mainframe and MIDI computers. Now, I have to say a big thank you to Don Tillman for the in-depth articles on the machine and a Java simulator which lets you try a virtual Muse out yourself. The links are on the screen and in the description below. And the Muse is a hardware music composition machine from a company called Triadex, and it uses binary counters and shift registers to generate patterns of notes, ranging from very simple to very complex. You could probably make something similar nowadays with modular synths using fancy clock divider modules, but this was a novel thing back in the day. The user manual is still available online, and it says, "The Muse is for tomorrow's music, music that has never been heard before." Now, unfortunately, it wasn't a massive hit, as apparently only a few hundred were made, but it's an intriguing and fun device to explore. At the core of Muse is a tone generator whose pitches are defined by 4 binary values, called intervals A, B, C, and D. If you remember from the hex video, number 3, 3 bits allow 8 possible values, so A, B, and C are mapped to the 8 notes of a musical major scale. The 4th bit, D, moves the note up an octave, giving a total range of 2 octaves. And the whole 2-octave range can be moved up or down in pitch with a slider. Now, with just these rules, the tone generator will play continuous notes, legato style. There's no rest. But there's some redundancy, as the 1st and 8th notes in the scale are octaves apart, and the D bit already defines the octave, so one of the 8 combinations can be interpreted as a rest. Some patterns sound better with a rest, others do not, so the interpretation can be changed with the rest switch. Now these 4 note-defining bits can be connected to various binary sources using these long slide switches. Each one has 40 positions. Right, here's the Plex simulation of Muse. The screen is a bit cryptic, I'm afraid, and I've used slightly different names for the switches, but it should be clear enough. Now, these first switches represent the 4 intervals, A, B, C and D, which I've called octave, and I've added an extra octave switch to increase the range. Now I've used numbers to represent the position of each 40-way switch, so the number here shows what that interval bit is connected to. In other words, its source. And there's a short description to clarify where that source bit is in PlasMa. Now the first 2 numbers, or connections, are fixed values of 0 and 1, which are shown as off and on. And this single step button tells the machine to play the note as defined by these switches. So in PlasMa's case, it will output the corresponding MIDI note. Now as I change the interval switches, you'll hear the different notes in the scale. Okay, and so on. The second part of the machine is the clock, controlled by the tempo slider on the Muse and shown by this number here. And the clock state on PlasMa is shown on bit 0 of register B. So we can see it change from 0 to 1 on the front panel and 1 to 0. Now this clock feeds 2 binary counters, which are also shown on register B. Now on the original Muse, one of them is a 4-bit counter, so its 4 binary bits provide clock signals divided by factors of 2. And my version uses a 5-bit counter to give more factors, and these bits are shown on bits 1 to 5 on register B. So each clock tick will tick the counter 1 step further on. And as you've probably seen me use before, this button resets the counters. Okay, the second counter fed by the clock is 2 bits long, and it's clocked every 3 beats. And this means its 2 binary bits provide clock signals divided by factors of 3. And this counter is shown on the next 2 bits, bits 6 and 7, on register B. So I'll tick the clock again. 1, 2, 3, and you can see the first bit of the 2-bit counters gone to 1, bit 6. 1, 2, 3. And then bit 7, 1, 2, 3, and now you've got both bits. Okay, all pretty boring so far, but the fun starts when we connect an interval switch to these clock bits. So if I connect interval A to the main clock, which is shown here as RB bit 0, that's my naming standard, and now tick. So the interval's toggling between interval A being set and interval A not being set. If I connect interval A to the first bit of the 5-bit counter, and tick. I'm doing 2 ticks for every change of note. Okay, we have another button here called play, which sets the clock running permanently. I'll set interval A back to the first clock bit. Then to the second clock bit. So it's halving in time each bit of this counter. Now if I connect intervals A and B to different counter bits, as we connect more interval switches, the patterns become more complicated, and some of them can sound quite musical, although maybe not at the moment, as the division factors of 2 and 3 create patterns which follow time signatures such as 4/4 and 3/4. These counter connections can generate interesting riffs for developing elsewhere, but they can get boring if you just leave them running. So Muse has a magic ingredient to provide more variety, and this will explain why those slide switches are so long. It uses a similar technique to some devices for generating random numbers. They're really pseudo-random, as they follow an algorithm and are repeatable, but they're perfect for this type of musical application. It's called a linear feedback shift register, which is just a fancy term for a register which shifts bits out from one end, these are lost forever, but the bits fed in at the other end come from a function which is based on bits from the shift register itself. Now this feedback creates a whole new set of chaotic but repeatable patterns within the register. In the Muse machine, the register is 31 bits long, and it's shifted on every clock beat. And the function which generates the input bit is an exclusive NOR gate with 4 inputs called W, X, Y, and Z, which are called the theme. And just like the intervals A, B, C, and D, these theme bits can be 0 or 1. Now the exclusive NOR function sounds complicated, but it just means that the shift register is fed with a 1 if the theme contains an even number of 1s, otherwise it's fed with a 0. Now these 4 theme bits have their own 40-way slide switches, so their values can be defined by any of the counter bits, which you've seen so far, or any of the 31 bits within the shift register itself. And this is why these switches have so many positions. And the shift register on PlasMa is shown in registers C and D, and also the accumulator. So you can see the patterns shifting from right to left and evolving. Now 0 counts as an even number, so when the theme switches are all set to off, they're all zeros, we'll expect a 1 to be pushed into the shift register. As we tick, you can see register D, and the accumulator has a 1 fed in from the right hand end. If we set one of the theme switches to a 1, the total number of ones on the theme switches is odd, so we'll now feed in a 0. And if we put in a counter on one of the theme switches, its state will change depending on the counter, which is clocked, and the shift register will see a different input bit at those clock times. So we're shifting in alternate ones and noughts. If I use a different counter, you can see the pattern is now changing to something maybe unexpected. There's 2 ons and 2 offs. And if we change one of the other themes to maybe a different counter, no difference there because they're probably in sync. So let's try a different counter again. And now we're seeing something quite different there. 4 on, 4 off. Let's just run it. Right, we're getting 4 on, 2 off, 2 on, 4 off, 2 on. So still a cyclic pattern, but a bit more varied than a straight counter bit. And as you probably guessed, those interval bits up here, A, B and C, as well as being able to connect to the counters, they can also be connected to bits from the shift register. So if we set this to the first bit of the shift register and run, and we can mix and match. We'll have another interval set to a counter. Okay, well I won't bore you too much more, but the number of permutations is now extremely large and the patterns can run a lot longer before they repeat. I've already mentioned an extra octave switch which I've added for experiments, but there are a few others. There's 2 switches for the scale. I've got a minor and a blues scale in there, but I need to experiment more with that. I've got 2 for the velocity, which gives a nice variation, a rhythmic variation to the pattern. And I've made the rest option into a switch. So you can choose to have rests within the pattern. Here's a quick example of the velocity. Let's get a pattern going. So there's plenty of scope. Okay, that's it for now. Thanks for watching.
you.